for your forward for your talk.
Wonderful. Sorry again.
15 minutes. Okay.
Sorry again because I was like in the gamma ray side at the moment. Yes, well, I'm Pedro de la Torre from Stockholm University. Thank you for coming. And in this talk, I would like to speak about the current predictions of anti-nuclei and their potential to reveal the existence of new physics. So I'm going to start with antiprotons, and in particular with what I call the spectral excess in antiprotons. As probably most of you know, from 2017, some researchers claimed the possibility of an excess of the data over the predicted fluxes of antiprotons that can be well accommodated from the production of antiprotons coming from a dark matter particle annihilating or decaying into hadronic final states. With time, this kind of analysis have been adding more ingredients and have been refined. And recently, researchers started to include more important ingredients and more complex analysis. In particular, we started to analyze antiprotons in combination with other secondary cosmic rays. This is important because this is done in order to ensure a better determination of the diffusion coefficient and the propagation parameters involved in the transport equation in general, and also to include the effect of system of cross-sections uncertainties in the determination of these propagation parameters. What we have found within these models is that we still observe an excess on the data over the predicted flux. But this time, this excess is featureless, at least in energy, meaning that what we observe is an excess that is a normalization issue, is an offset. And in fact, this implies, as you can see from the dashed line, that with a renormalization of our flux by a 10%, the energy dependence of the antiproton prediction is in perfect agreement with the one measured by AMSO2. And at the same time, we are reproducing boron, beryllium, and lithium secondary cosmic rays. This 10% is totally compatible with cross-sections uncertainties on antiproton production, since the estimations are that these cross-sections uncertainties are of around 20%, and they are roughly constant, so that this offset is well explained by these cross-sections uncertainties. More recently, I have tried, or my colleagues and me have tried to improve a little bit further this kind of analysis, including a lot of ingredients, and in particular, including also nuisance parameters, scale factors as nuisance parameters in order to renormalize the cross-sections of antiprotons, boron, beryllium, and lithium. These scale factors have associated with them prior constraints that come from cross-sections data, which are mainly a penalty factor that prevents our scale factors to modify our original cross-sections a lot. Okay, and from this kind of analysis, we still see the same. We have an offset with respect to antiprotons that is solved with around 9% scale on antiproton cross-sections production, and the energy dependence is perfectly reproduced for all the secondary cosmic rays that we include in the analysis. However, still, it seems that when we include in our analysis a possible production of antiprotons from dark matter, this dark matter component, or this, the inclusion of this component is statistically preferred. Statistically preferred with a significance that is even below 1 sigma. So this is not even a hint of any feature in the proton spectrum. Something interesting that we have seen here is that the scale factors for antiprotons and the other secondary cosmic rays slightly affect the properties, or the properties of the dark matter particle that is inferred. Particular here, I'm showing you the results for an analysis in which we include all the the prior constraints, all these penalty factors associated to the cross sections for boron, beryllium, lithium, and antiprotons, and compared to the case in which we do not include any penalty factors. So these scale factors to renormalize the cross sections of the secondary cosmic rays are totally free to scale. And as you can see, well, the properties of the dark matter candidates are different, or are slightly different, but they are not very different. But for sure, let me skip this slide. This does not imply that we are controlling, or that we have under control all the systematic uncertainties in our predictions, because we are assuming a very naive scenario where antiprotons can only be produced from cosmic ray interactions, what is called the secondary contribution from cosmic rays, or from dark matter producing antiprotons. The problem is that we are missing a lot of possible other options. For example, that antiprotons are accelerated in sources, in supernova remnants. And in fact, this is a nice idea, because it could explain also the coincident high energy slope of positrons and antiprotons. On the other hand, something that can be even more naive is the fact that our models, or at the moment, the analysis of antiprotons have been restricted mainly to models in which the diffusion is constant everywhere. And we have very good theoretical reasons that support that the diffusion coefficient is completely non-uniform. And this is important because in 2016, there was the authors of this paper here demonstrated that in a model in which the diffusion is different in the halo and in the disk, because, well, they are two different plasmas, so the diffusion is expected to be different in both plasmas, the predicted antiproton yield is increased with respect to the typical predictions with the diffusion coefficient that is constant. And this kind of theory, well, in particular, this kind of model can offer also an explanation for the dipole anisotropy, but I don't want to discuss that. What I mean with this is that we are far from understanding all what is happening, that all the possible sources of antiprotons here, and the transport of antiprotons in general. And this means that probably it is going to be very difficult to find signatures of dark matter in antiprotons, at least not until we improve our understanding on the transport of cosmic rays in the galaxy. But here is where anti-nuclei can play a very important role, because we expect that the dark matter production of anti-nuclei is different and well separated from the production of anti-nuclei, anti-helium, or anti-deuterons coming from secondary from cosmic rays colliding with the interstellar medium. Okay, and this is very exciting because at the moment AMSO2 has already some candidates, a few candidates, up to 9 candidates for anti-helium and up to 7 candidates for anti-deuteron. And this is very exciting. Let me show you here in this plot different the production for anti-deuterons of different dark matter masses with a cross sections with an annihilation rate which is close to the thermal annihilation rate. And as you can see, all these different masses of dark matter that are compatible with masses coming from some hints or excesses in the astroparticle scene, they can be observed by the AMSO2 and gaps. The different lines here, the solid line and dashed lines, represent different setups of the hadronization and the coalescence of anti-deuterons coming from BB bar final states. But this is very interesting because it would allow us, a good detection of anti-deuterons would allow us to prove or discard many different excesses. What we see from our analysis, from this kind of analysis of antiprotons that I have been showing, is that we, in this, let's say, for this dark matter that is predicted or inferred from this analysis, it can be observed by AMS. But also, what is also very interesting is that also the secondary anti-deuterium could be observed in the next few years by AMSO2. And this is something really exciting, okay? This could be the first real observations of anti-deuteriums. For antihelium, the situation is a little bit less promising, let me say, because our predictions imply or predict like 1 order of magnitude less than the sensitivity that AMSO2 have. But however, AMS has reported some candidates. And a possible explanation of this can be, in fact, in this peak that you observe here around 10 GeV in antihelium production from dark matter. This peak comes from the production of lambda B particles and substrates and the proceeding and the decay of these lambda B particles on antihelium. And the fact that the branching ratio of production of lambda B particles can be much higher than the one that we usually assume, and I am assuming here. Okay, so it will be very important, the confirmation of the amount of events in AMSO2. And this drifts to my conclusion. I think I have done it more or less well with time. At the moment, our predictions are very limited by our limited understanding of the propagation of cosmic rays. And in fact, antiprotons will hardly be used as a well, to spot the existence of dark matter. Even within the naive scenario that diffusion is the same everywhere, and only dark matter or cosmic rays can generate to AMSO2 data. And well, finally, let me say that anti-nuclei seem to be a very promising tool, but we need still to be sure that the measurements that the candidates that we have are real events of anti-nuclei, and we still have to work a lot on our models. So that's all. Thank you very much for your attention.